Okay, welcome back. This is the last session of the workshop, and our first speaker is Can Kozcaz from Boğaziçi University. Thank you.
Okay, thank you very much. It's an honor and privilege to be able to talk in this memoriam workshop for Durmuş Hoca. I met him when I was a postdoc at CERN, and he was frequently visiting, interacting with both theorists and experimentalists. So we had a number of conversations with him about physics and other things. And his enthusiasm about physics was really contagious and inspiring. And I always enjoyed our conversation. And I think he's one of these physicists who was really about doing good science and understanding fundamentally physics and nature. So I hope he could also have a chance to listen to our work. I'm sure he would appreciate it. And we dedicated our last paper in his memory. Unfortunately, we lost him. So while we were preparing this paper, so I'm going to talk about something very simple, actually. I'm talking about solving Schrödinger equation. This is something you all know from quantum mechanics courses, but we are trying to do it in a little bit more sophisticated way. But at the end of the day, we are solving Schrödinger equation. And in general, okay, there are different ways you can quantize the system, and one of them is putting or formulating your theory in terms of path integral. And you can compute expectation values, correlation functions for observables. Unfortunately, there are a very few models or very few theories where you can actually solve the theory exactly. Otherwise, you have to do approximation methods. And one of them is perturbation theory, right? Or self-point approximation. And the perturbation theory is essentially what we do in all undergraduate study. And later, we also start talking about self-point approximation, the path integrals. And there is a problem with perturbation theory, and that is when you compute the perturbative series, they are usually asymptotic and they are divergent. So if you are trying to calculate an observable and want to give your experimentalist friends a prediction, this number better be a finite number. Okay, if it's infinite, it's meaningless. Okay, and actually we can trace down the source for the divergence in the perturbation series. And that's related to the fact that, naively or heuristically, that the number of Feynman diagrams at increasing orders is increasing factorially. If you assume that each diagram is approximately of the same order, giving same order contribution, and if their number is increasing exponentially, that's an asymptotic series. And if you look at almost any textbook in quantum physics, you will see a graph like this, where the perturbative approximation is getting better and better. Okay, you even calculate the optimal number or the order in the perturbation series that you can keep, and then they tell you, let's throw the rest. Okay, because that's going to cause you these unwanted divergences. And you can also do some numerical computation, and you can really see that the high order terms are increasing factorially. But the question is it really a good idea? I mean, do we really need to keep, or do we really have to throw all this infinitely many terms in the perturbative series? Is there any chance that this infinite number of terms in the rest of the perturbative series has any meaning? And the answer turns out to be, we better keep it, because back in the day, in 60s, so it was at the end of 60s, it's that late, Bender and Wu showed an amazing result. They showed the large order behavior, meaning this divergence in the perturbative series, is controlled by the leading contributions of the non-perturbative sector. And here, when I say non-perturbative sector, it may sound fancy, but especially if you're talking about quantum mechanics, it's nothing but tunneling. And this should be surprising, because tunneling and perturbation theory seem to be uncorrelated. However, their results show that actually these two separate sectors, or seemingly separate sectors, are intimately connected to each other. And of course, one thing you can do if you have an asymptotic series like the perturbative series we have, to Borel sum them or to employ any other resummation techniques. But if you do that, the answer you will get is ambiguous and complex. And this is a problem. For example, imagine you are computing perturbatively the eigenvalues for energy and you find it complex. Okay, so you cannot measure a complex energy. You are expecting your energy eigenstates to be real numbers. So because of that, okay, I'm not talking about decay. Let's say we have a stable system which doesn't decay. So we are expecting the spectrum to be real. So the Borel's transform for this asymptotic series is not, or it needs to be done something to it. And in 80s, the mathematician named Ekal came up with a beautiful theory called resurgence theory. And he said, actually, instead of considering what we call the perturbative series, let's try to consider something a little bit more involved, which includes also non-analytic functions. So, and then you can get an ambiguous answer, and I will get to and try to explain to them. So then what we want, okay, is to understand perturbative and non-perturbative sectors. And again, you may expect them to be unrelated, but I will try to argue today, based on the work by Dunn and Ünsal, that actually the perturbative and non-perturbative sectors are very much interconnected. And about 10 years ago, Mithat Ünsal and his collaborator Gerald Dunn came up with an answer, and I will try to explain what all these numbers are. Kind of argued that knowing the perturbative series, you can construct the non-perturbative contributions coming from phenomena like tunneling, and ultimately you can solve the spectrum. So our goal is to, given a potential, which is not exactly solvable, try to find the spectrum. Okay, and the spectrum will also include some non-perturbative contributions. So what do I mean by trans-series? Or what do I mean by this, like, more general non-analytic expansion, including the non-perturbative phenomena like tunneling? So if you have energy, so you want to compute this at some level n, so you have the usual perturbative series. This is something, textbook material, that you can open any quantum mechanics textbooks and they tell you how to compute order by order these numbers, okay? And then we have what we call the instantons sector. So you can imagine the instantons as tunneling. So this stereotypical example is double well with degenerate minima. So if you prepare a state around one minimum, eventually that particle will tunnel to the other vacuum and back. So it may go back and forth. And that's why we need to sum over n, how many times they cross the barrier, okay? And if you have more than one instanton, okay, they usually interact with each other. And they also have some logarithmic contributions. And these are the coefficients that we are after. So these are quantum fluctuations around like instanton background with some interactions, okay? And we want to compute this coefficient. So this is going to tell us what the energy levels are, okay? You may say, well, you may look at this and say, well, here the instanton contribution, so this is instanton action. So this instanton action is e to the minus s, some number, divided by h bar, okay? And you can say, well, if h bar is small, so this is going to be exponentially suppressed, especially compared to the perturbative part. So you say, why don't we ignore all this together? I mean, this is very, very small compared to the perturbative part. And that would be a mistake, because even if you want to solve the simplest problems like the double well and rely only on the perturbation theory, you cannot distinguish between the energy splitting between the ground state energy and the first excited state. So perturbative theory will give you a degenerate ground state. Or you may have supersymmetric versions of quantum mechanics where the ground state having zero energy or not is crucial to understand supersymmetric breaking. And as we have seen today a number of times, supersymmetry is broken. And we really need to know how it's broken, at what energy scales it has broken. So in that sense, even in the simplest models, we really want to understand a way to see how the supersymmetry breaks. And sometimes there are cases where the ground state energy is vanishing perturbatively to all orders, but you may get a non-zero contribution from the instance sector, which actually is responsible for the symmetry breaking. So the simple, naive, comparison between the perturbative part and the non-perturbative part may lead us to have a wrong interpretation of the dynamics of the system. So because of that, it's really important to be able to understand this instance sectors, okay, or the contributions to the energy. Okay, and okay, this is a small remark. So you see this actually starts with 2 because you can't, instanton doesn't interact with itself. So you need to have at least 2 instantons to start talking about their interactions. Okay, so then the question is like, how do we determine these coefficients, right? This E ends, okay? And Zinjassin and Yanshura about 15 years ago, and it's actually surprising to me, this is a very simple problem that could have been probably solved when Schrödinger wrote down the equation, but it took almost 100 years to really find a method to, solve this energy spectrum precisely. And they came up with something called the generalized quantization condition. And you may remember from the previous slide, there are 2 functions, B and A. They appear in this equation. And I will tell you what they are in the next slide. But they satisfy a condition. And this is quantization condition because if you know what A and B are, and B encodes, as I will tell you in the next slide, the perturbative information, and A, on the other hand, decodes the non-perturbative information. If you know B and A, you can solve for A order by order and determine this coefficients E. So this condition after calculating A and B tells you what the spectrum is, okay? And this condition is actually nothing but a generalization of the Borzamorfeld quantization, which I will remind you next. So here is an example, as I mentioned, the stereotypical example is the double well. So B is, you can calculate it, and I will also show you how you can calculate it. So B is an expansion in H bar in terms of the energy. A is a similar expansion. And here, what you can do is you can invert this function, the series, write E in terms of B. And the funny thing is, if you substitute for B, n plus a half, and this should be familiar from the harmonic oscillator energy levels, because the problems we are dealing with are having degenerate harmonic vacua or minima. So if you invert the series and substitute for B n plus 1/2, this is nothing but the usual Schrödinger-Rayleigh perturbative series that you compute. On the other hand, the computation of A can be very involved, especially if you want to go back to the principles of path integral and want to solve it through there. I don't want to go into details. And you can see why, you can ask why it's non-perturbative. One way to see it, this 1/3, it's not just a regular or random number, but it gives you precisely the action of tunneling, right? If you go and pick up Coleman's book, look at the instanton contribution, you have the inverted potential. So it goes from one maximum to the other one. You can find the equations of motion, solve it, plug into the action. That's the number you get. So that actually, this series knows about tunneling, okay? And you need to compute them. If you know them, you plug into this equation I mentioned, you can get the spectrum, okay? And as I said, this is generalization of Bohr-Sommerfeld quantization condition. So as I said, let me remind you. So if you have a potential like this, you may say, okay, I'm looking at an energy which is, somewhere here below the asymptotic, values, or if it's like unbounded, going to infinity, it can be any energy. So it may have two turning points. And the particle classically will oscillate back and forth, and you can compute this quantity. So the classical mechanics tells you the particle can have any arbitrary energy it wants, depending on the initial conditions you impose. But quantum mechanics or Bohr and Sommerfeld tell you, well, if the particle is oscillating and is tracing a curve on the phase space, this area enclosed by the curve must be an integer multiple of h bar. So it cannot have any arbitrary energy. It cannot close any area on the phase space. It must be quantized. And that actually leads to the quantized spectrum. Okay, so basically what I showed you before, this complicated equation involving gamma functions and all this A function, B function, is nothing but some generalization of this if you have also tunneling. Okay, so if in this case, that quantization condition reduces to a regular one, and you can get the spectrum easily. But we want to have some non-perturbative contributions. So how do we do that? So in the title, you may have seen I'm talking about genus 1 potentials, and we will eventually come what I mean by genus 1 potential. So one way to see this quantization is, okay, so let's start with the simple harmonic oscillator. So we have the parabolic potential. We just cut it at energy. And associated to this, if you employ the WKB method, and we are going to use the framework not to the leading order, but the full exact WKB method, you can actually construct the wave function by drawing the Stokes graph associated with that potential. So this is a little bit technical, but essentially, if you write down the momentum, right, in terms of the energy and the potential, you have a square root. So you will have a branch cut associated with each turning point when the potential is equal to the energy, when the kinetic energy is vanishing. So you have the turning points, right? This A1 and A2. So it has a branch cut, and these are the rays or the directions in which the exponential behavior is either, increasing to infinity or decreasing to zero. So this is the graph encoding the behavior of this wave function when you substitute in the WKB the wave function as e to the something, e to as a function. And this encodes this complex behavior. And actually, if you focus on one of the turning points, it is usually Airy type. At least for the potentials we are going to consider, it's Airy type, and it means it will have some monodromy. So what it means, essentially, okay, I come back to this later. What it means is I can write my wave function as a doublet, a part which is exponentially increasing in a given direction and exponentially decreasing in some other direction. And when you are around one of these turning points, you have matrices, monodromies, which will mix these two components. So if you want to take H bar and rotate, make H bar complex and rotate it 2 pi, then obviously the behavior of the wave function is going to change. And every time you cross one of the Stokes lines, so these components are going to mix, okay? And what it does is, for example, if you solve the problem for the double well, you have and assuming the energy is below the maximum in the middle, so you have a little bit more complicated Stokes graph. And Mithat and his collaborators show that you can actually try to construct a wave function from going one direction to the other, impose this monodromies as you cross the Stokes line, and use some normalizations, NAB. So you can construct this wave function, and this quantization condition is nothing but the condition that the wave function is normalizable. So, okay, the upshot is, I mean, these are, I involve some technical details, but at the end of the day, what you want to do is, given the potential, you can draw a graph like this, which you can use to construct the wave function. We want to find the wave functions for the potential, right? And using some complex analysis, you want to get the wave function that can be normalized. So we have the probabilistic interpretation. Okay, so if you impose a condition that the wave function must be normalized, the condition you get is nothing but the condition Zinjasin and Yenchura gave you. And it involves some integrals, some normalization going from one turning point to the other. Okay, and so these are integrals. Okay. Okay, so let's come to the, point why we are talking about genus one, because as I said, if you write down the energy conservation, you have P squared is equal to energy minus the potential, right? You need to take a square root. If you do that, you have two Riemann sheets. So here are my Riemann sheets. And for the double well, for example, it's a quadratic function. So we know that it has 4 zeros. So these are the turning points. And there are branch cuts. So here is my branch cuts. And the two sheets are connected to each other through these branch cuts. So if I just go from here, then I just go and continue on the next sheet from the branch cut. And another way to think about this is basically gluing this, imagine them like slits and glue them together. So it means I'm taking these two sheets with cuts and turn them into two necks, connecting these sheets. And now, if I also do some compactification, that surface looks like a torus. And this is the genus one curve I'm talking about. So I can start with the potential, do this, imagine these cuts and gluing them together, and then I end up with a torus. So if you go to higher order potentials, higher degree potentials like sextic, right? So you will have 6 turning points. So it means you will add another cut, which you can also glue between the two sheets. So that will correspond to a genus 2 curve. And as the degree of the potential is increasing, so the number of branch points is increasing too, or the cuts, and you will have higher general curves. But we are focusing on the genus 1 curve now. And this, integrals you need to perform in the WKB analysis, they are related to the reduced action in classical mechanics of oscillations around the minima, which correspond to cycle integrals around this torus. And you have tunneling that's related to this type of integrals, and they correspond to the other cycle on the torus. So what we have done is we try to solve these periods. These are called periods. And using those periods, you can actually construct A and B. Okay? And they can be solved with using Picard, what's known as the Picard-Fuchs equations, and you can get, A and B. Okay, so this is well established that you can do. But the interesting thing is what Dunn and Unsal proposes. They said, well, let's observe something, or let's try to have something simpler. And they said, okay, so this A is the non-perturbative part. Okay. And so this is E and B is the perturbative part. And they say, knowing only the perturbation series, so if you just solve this equation and solve this differential equation right as an integral, so knowing the perturbative part, knowing the undergraduate level of physics, you can obtain the non-perturbative part, this A function. So the function that's hard to get. Okay, so this is amazing because it kind of shows you, if you forget about all the things we can do, knowing perturbations perturbative theory, you can get in non-perturbative physics. You can ask, why is it useful? For example, we can think of a theory which has only a perturbative definition, like string theory. String theory doesn't have a well-established non-perturbative definition. We define it in terms of a perturbative series. So this type of method, although this is very like, it's a baby version obviously in this form, takes us from perturbation theory to non-perturbative physics. So if we can push these methods that we develop in quantum mechanics to higher theories, and people have been trying to do that in matrix models, in topological strings, but if you can apply also to more dimensional field theories, then eventually you can rely on the perturbative series to understand non-perturbative physics. And this is also another remarkable result, because the usual resurgence, the one I mentioned, or this usual relationship between Bender-Wu found or Ekal developed, is about large order behavior and low order behavior. This relationship is low order to low order. So you don't need to calculate some large order behavior. Even if you know the first few orders in the perturbation series, that will give you immediately the same order of contributions in the non-perturbative physics. So what we have done is we said, okay, all the examples so far were only studied for specific examples of genus 1 type potentials. We said, let's use a 1 or 2 parameter class of potentials. So people have checked, Kemal and Ilmar have checked for quartic. They also check for cubic. Now, what we have found is some interpolation between them. So this is a family of potentials that you can study. And if you graph them, the potentials look very different. And why is it important? Because they are interesting things. You have some real instantons and also what I call the complex instantons. And let me say a few words about this. If you open Coleman's book to calculate instantons, he will tell you to disregard this type of instantons, because he will say, if you put the particle here, it will roll either minus infinity from left or from right. It will have infinite action and they don't contribute because it's going to be e to the minus infinity. But what he was missing is, and Mithat and his collaborators proposed it, and we showed that actually it works in a subsequent paper, that you have to take into account the holomorphic version of the Newton's equations, and they have complex finite action solutions, and they also contribute. But that's a whole other story. So, but this deformation allows us to interpolate between this type of real instantons that Coleman allows, and this other type of instantons which he doesn't allow. And our formula interpolates between both. And that's the answer we found. So we said, okay, this relationship, which is also known as the PMP relation, can be generalized depending on the deformation parameters. And it looks ugly. Okay, we published it, but we didn't know any better. We found this is a great result. We published it. But then we keep working on it. And two things. First of all, it looked ugly. The second is, do they have a meaning? Okay, these coefficients that appear in this expansion. And fortunately, we answered both of them affirmatively. And what we have found is, you may define not only polynomial potentials which depend on a parameter, but you may have, 2 minutes, which you may also have other potentials like Sine-Gordon potentials or elliptic potentials in the Lamé systems, which are studied also in condensed matter physics because they exhibit band and gap structures. And what we realized, and I think this was a nice observation, there is actually a universal parameter that's defined by the problem. You can deform a potential in the way you want. I can deform it in another way. So our deformation parameters may be completely unrelated. But the theory tells us, okay, compute the residue at the pole of the potential. So it could be at infinity, like polynomial potentials, but it could be also at a finite point for elliptic potentials. And if you write all the deformations in terms of this residue, the PMP relationship, so this ugly expression that I showed you simplifies to this very compact form, which you can also write like a little bit more explicit like here. And this is true for not only polynomial potentials, but also for like potential, like which includes sine, cosine, or elliptic ones. Okay, so this is kind of universal form for the relationship between this non-perturbative function A and perturbative function B. So from perturbative series, we can get the non-perturbative result. And one thing I want to emphasize and then finish is this is not just putting a single parameter and let's, for example, this is the instant on action, looking at everything, oh, now S is not a constant, but a function of the parameter. No, it involves also the derivatives, which you would miss in general by just like, substituting the action with like, a parameter dependent action. Okay, and we also checked, so this is, and this also obviously returns when the residue is 0, back to Daniel-Sal relation, PMP relationship. Since this is a partial differential equation, it requires a little bit more. And for the sanity check, we also checked the numerical computations for the energy and how, like, the leading and sub-leading contributions that we can find from this PMP relationship are correcting the spectrum. So here one is, these are the ratios. You see, the leading behavior is the blue one. You include the sub-leading, it becomes the orange one, and it becomes like, the red one. So we are doing something really meaningful. Okay, so thank you.